Scene 1, the compound interface and multi-beam superposition. Welcome to the second lecture of the Wave Mechanics of Microwave Absorption series. In our previous lecture, we rigorously derived the reflection and transmission coefficients of an isolated interface boundary, proving they are constant properties Rm independent of sample thickness d. But what happens when we transition from a zero-thickness interface to a practical film with physical thickness d? Here lies the fatal theoretical error that has governed materials science for 50 years, the confusion of the film with the material, and the conflation of the interface with the film. A film is not merely a material, it is a physical device bounded by two parallel interfaces. To describe the microwave reflection of a film, commonly known as scattering parameter S11, we must move beyond isolated interface properties. We must account for the infinite superposition of waves reflecting back and forth within the two boundary interfaces. Let us prove this through two independent, mathematically rigorous methodologies. Scene 2, Method 1, the infinite geometric vector summation. Our first derivation path is the microphysical approach, ray-by-ray wave superposition. We trace the path of each individual wave as it undergoes internal reflections inside the film. At the front interface, the wave is partially reflected directly back to space as Rm. The transmitted part penetrates the film, experiences a propagation phase and damping factor J_gamma_d, reflects at the rear interface, characterized by rear reflection coefficient R, rear, and travels back. Upon hitting the front interface again from the inside, it partially transmits back to space as a second ray, while the rest reflects back inside. By writing down this infinite geometric progression of waves escaping from the front and summing them to infinity, we obtain the rigorous formula for the film's scattering parameter S11. For a film without metal backing, WMB, placed in empty space, where R, rear, equals Rm, we get S11, x1 caret. And by summing the transmitted portions escaping through the rear interface into the back medium, we derive the transmission coefficient S21. This elegant vector summation is documented in the appendices of Yulu's critical treatises of 2021 in the Journal of Microwave Power and Electromagnetic Energy, as well as section 4.2.3 of Thomas, Paoloni, and Pye's 2024 Elsevier monograph. Scene 3, Method 2, the macroboundary continuity. Is there another route? Yes, the macrocontinuous route using classic transmission line boundaries, as authored by Yulu in Physica Scripta 2022, Appendix A2 and A3. By representing the fields inside the film as the superposition of a single total forward wave Fm and a single total backward wave Bm, we establish two boundary nodes, x1 and x2. By writing down the continuity of total voltage and total current across both nodes simultaneously, we establish a system of linear equations. By solving this system using middle school matrix mathematics, we arrive at the exact same expressions for S11 and S21. Furthermore, this continuous boundary path naturally yields the film's complex input impedance, Zin for a metal-backed film. Behold the absolute unity of physical science. The ray addition perspective and the node boundary perspective converge perfectly, validating each other without a single shred of ambiguity. Scene 4, the metal-backed collapse of impedance matching. Now, let us apply this rigorous wave mechanics to the most common configuration in materials research, the metal-backed film. Because the metal backing has a characteristic impedance of metal equals 0, its interfacial reflection coefficient is fixed at exactly rear equals -1. Plugging this into our wave mechanics formula immediately yields the textbook reflection coefficient RL of a metal-backed film. Look closely at this formula. Academic journals have claimed for 50 years that a minimum in RL means impedance matching or Zin equals Z0, implying that all microwave energy penetrates without boundary reflection. But this is completely false. A minimum in RL is not caused by the interface disappearing. It is caused by destructive interference, namely, the ray reflected from the front interface Rm is out of phase by exactly pi with the rays reflected back from the metal interface, cancelling each other out in the open space. Impedance matching is an interface property. Wave cancellation is a film device property. By misapplying RL to characterize material properties and ignoring basic boundary superposition, modern materials science has built a half-century-old card house of false theory. We do not need peer-reviewed consensus to protect illogical errors. We need to reclaim the absolute primacy of classic wave mechanics over mainstream academic bubbles. Read Yulu's master treatises in Physica Scripta and Materials Chemistry and Physics, and subscribe to his Substack. Reclaim the theoretical foundations. Thank you for watching.